So today we're going to learn about probability. In many textbooks, probability and counting is an entire chapter on itself. Here it's combined into just two sections, and I mean there are even uh, entire courses on this stuff. So we're going to kind of hit the high points of 10.7. We won't necessarily be quite so thorough. It's a pretty long section, but basically we just want to make sure we understand the some of the basic concepts and how to calculate some probabilities. So. The empirical probability of an event E, denoted by P of E, is basically the number of times E happens so number of times E occurs over the total number of occurrences. All right, so you just take, like, again, if I flip the empirical probability of getting heads, if I flip a coin 10 times and I get 7 heads, the empirical probability would be 7 out of 10, because that's, empirical means basically, tested. So I've actually gone through and tried it out and seen what I had it. We'll talk about the theoretical probability in just a second. But um, so express probabilities as fractions and as decimals rounded to 3 decimal places. Find the probability that a woman aged 40 to 49 has a positive mammogram. All right, so um, if we're looking at this, we've got 100,000 women got screened. So the number of women that have a positive mammogram is going to be, we had 720 that had one and had breast cancer, and 6944 that had one with no breast cancer. So we're going to add those together. So we can just do 6944 plus 720. We're going to have 7664. Not sure why I broke out the calculator for that, but and then we're going to divide by 100,000. So um, basically, if I divide by 100,000, basically move the decimal spot over 5 different times. So I get 0.07664. Among women with breast cancer, find the probability of a positive mammogram. So with breast cancer, that's going to be looking at this column. So that's 800 is the total number of people that have, women that have breast cancer. And how many that had a positive mammogram? 720. So 720 divided by 800. So that's, well, I mean, that's just 72 over 80, um, 36 over 40. Maybe we can keep on reducing. I guess that's 9/10. So 0.9. Among women with positive mammograms, find the probability of having breast cancer. So with positive mammograms, so that's again, that's looking at these guys. So we had 700 or 7,664 that had a positive mammogram, and of those, 720 have a mammogram. So or have a have breast cancer. Sorry. So I get 720 divided by 7664, and I get 0.093 or 0.094. And I didn't really follow directions up here. I should probably have just done 0.077 because that's 3 decimal places. All right, so probability, really the hard part comes into the counting part of probability, the stuff from 10.6. So right now it seems super easy, and probability can basically be as hard as you want it to be. Like if we start talking about what's the probability of getting uh, two pair or something like that in a hand of poker, then it starts to get a little bit harder to calculate those types of things. We're not going to quite go that difficult. All right, so theoretical probability. If an event E has n of E, that's basically the number, like n I think of as the number of ways it could happen, equally likely outcomes in the sample space S has n of S equally likely outcomes, then the theoretical probability of the event E denoted by P of E is n of E over n of S. And so really it's just a kind of number of desired outcomes and number of possible outcomes. That's kind of how I think of it. So again, back to the coin example. If I flip a coin 10 times and I get heads 7 times, the empirical probability was 7 out of 10. However, the theoretical probability is we have two options, heads or tails. They're both equally likely, and so the probability of getting heads would be 1/2. So that's kind of the difference between theoretical and empirical. Empirical is looking at data that we've already has occurred, and theoretical is what we would expect to happen kind of in the future. All right, so some key terms we got to learn here. An experiment is basically anything that where the outcome is uncertain. So an occurrence in which the outcome is uncertain. And then the sample space is basically all the possible outcomes. So like if I'm flipping a coin, the sample space would be heads or tails. And the event E is just basically it's a subset of the sample space. It's what we want to, what we're checking whether it happens. So a subset of S. Yeah, so I guess the best way is, as an example, experiment might be flipping a coin. Sample space would be getting heads or getting tails, and the event E we might be looking for is the probability of getting heads, where we're taking one of the possible outcomes. So here's another example. A die is rolled, find the probability of getting a number greater than 4. So the sample space is we could get a 1, a 2, a 3, a 4, a 5, or a 6. So the number of, so n of s, that's just the number of outcomes we could possibly have. That's 6. Probability of getting this event happen, well, that's 1, 2, the 1, 2, and 3, right? We could have a 4, 5, or 6, so that's 3. Oh, sorry, let me write that. That's kind of a different order than I was expecting. So 4, 5, or 6, so n of e equals 3. So probability of e happening is 3 out of 6, which is 1/2 or 0.5. Now, one thing to note, probability should always be between 0 and 1. 0 means it never happens, 1 means it always happens. So you can't have a probability of 2. That's like saying flipping a coin once and I got heads twice. That's just not going to happen. So, so probability is always between 0 and 1. So what is the probability of getting a sum of 5 when two 6-sided dice are rolled? So here's a nice diagram of all the possible outcomes we could have. So the first die could get a 1 through a 6. The second die could get a 1 through 6. From 10.6, that means there are 36 possibilities. 6 times 6 equals 36 possibilities for how the dice could end up. And now we're looking for ones that have a sum of 5. So if we look at the ones that have a sum of 5, they're everything in this diagonal row. So if we look at this, we saw that there were the sample space. I already showed that was that, you know, 1 1 2 1 dot 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 6 1 1 2 dot 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 1 6 6 6. That was that diagram. That's that whole. And E is basically the set. We said it could be 1 4 2 3 3 2 or 4 1. And so when I look at that, I get 4 over 36, which is 1/9, or 0.111. All right, so you are dealt one card from a standard 52-card deck. Find the probability of being dealt a king. So the number of kings in a deck are 4. The number of cards in a deck are 52. So it's 4 over 52 equals 1/13. Find the probability you are dealt a club. So in this case, the number of clubs is 13. The number of cards is still 52. So I get 13 over 52, which is 1/4. Otherwise, you could say, well, there are 4 suits. They're all equally likely, so it's 1 out of 4. Both of those explanations work. All right, so Powerball is a multi-state lottery played in most U.S. states. It is the first lottery game to randomly draw numbers from two drums. The game is set up so that each player chooses 5 different numbers from 1 to 69 and one Powerball number from 1 to 26. Twice per week, 5 white balls are drawn randomly from a drum and 69 white balls numbered 1 through 69 and 1 red Powerball. All right, so a player wins the jackpot by matching all 5 numbers drawn from the white balls in any order and matching the number on the red Powerball. With one $2 Powerball ticket, what is the probability of winning the jackpot? All right, so first off, let's figure out the number of successes. Well, there's only one winning lottery ticket, right? You match all the numbers, so there's only one success. Now the harder question is how many different lottery tickets can be sold? And the answer to this is if we have 69 white balls and we were choosing 5 of them and there's no duplicates and the order doesn't matter, well, that's going to be 69 choose 5. And then we have 26 red balls, of which we're picking 1. So that's, you could say 26 choose 1 or just 26 is the same thing. So that's our denominator. So we have 1 over, and if we just do 69 C5, let's take it times 26. We get 292,000,000. 292 was it 201,338. And so that's a very, very small probability. 1 divided by the answer. Oops. So 0.00000003. Right? So I mean we're talking a very, very small percentage. And let's actually just check this on the website. They have to have the odds listed on the website. So let's just pull that up real quick. So this now I'm on the actual Powerball website, and you notice the grand prize. It says 1 in 292, 2001, 338. So you can kind of see that this is exactly how you can figure out the probability of winning a lottery, the lottery with a lottery ticket. And then there's another concept in probability called expected value, where you can see how much you would expect to gain or lose on a given, with a given game or lottery ticket or whatever. But generally speaking, it's a losing proposition, right? 1 out of 292 million, not real good odds. So probability of an event not occurring. So the graph alongside shows the distribution by branch and gender of the 1.43 million active duty personnel in the U.S. military in 2003. Numbers are given in thousands and rounded to the nearest 10,000. If one random person is randomly selected from the U.S. military and the distribution is the same as it was in 2003, find the probability that this person is not in the Army. All right, so these are in thousands, so there's 1,430,000 people here. Now, one thing you could do is you could find out, find the probability that person is not in the Army. I could do 300 plus 70, right? Plus 170 plus 10 plus 320 plus 60. I could do all of that over 1430. So 370, 440, 540, 550, 850, 870, 930. So I get 930 over 1430. So I get 93 over 143. Or the alternative would be I could look at it and say, what's the probability of not in the Army is the same as 1 minus the probability that they are in the Army. So I could look at this and say, well, how many are in the Army? There are 420 plus 80 gives me 500. So I'm adding those two numbers. So I get 1 minus 500 over 1430, which, what do you know, is 93 over 143. And that's the easier way to do it. So a lot of times saying not is the same as saying 1 minus the probability of it happening. All right, so if A and B are mutually exclusive events, we just get to add the probability of A and the probability of B. That's only if they are mutually exclusive. Okay, so if they can't both happen at the same time, that's what it means to be mutually exclusive. If one happens, the other one doesn't happen. So, and similarly, I mean the set notation, this represents or, the union represents or, so I mean it's the same answer, but it's just a different way of writing it. So or union, same thing. And if we, another way is if we have and, that's the same as intersection if we use set notation. So again, mutually exclusive, it just basically means they can't both happen at the same time. All right. So if you roll a single six-sided die, what's the probability of getting either a 4 or a 5? So the probability of getting a 4 is 1/6. Probability of getting a 5 is 1/6. The probability of 4 or 5 is going to be 1/6 plus 1/6, which is 2/6, which is 1/3. What if you wanted to find the probability that a randomly selected card from a standard 52-card deck is a diamond or a face card? So these are not mutually exclusive, right? Because you can be a diamond and a face card if you're one of these guys over here. So just for those not familiar with cards, there's 13 cards in each suit, the suit being diamonds, hearts, spades, or clubs, and the face cards are the jack, queen, king. So there are 3 face cards in each of them. So notice, if we were looking at the diamonds and we want to say, what's the probability it's a diamond or a face card? Well, there are 13 diamonds here. That's that circle right there. And there are 12 face cards. So you might say, well, 13 plus 12, you know, out of 52 equals 25 out of 52. You'd think that might be our answer. But notice the problem is that we've counted these guys twice. So we need to subtract one of those sets of those numbers. So I actually need to instead do 13 plus 12, and then I got to subtract the overlap. So I end up with 22 out of 52, or 11 out of 26, and that ends up being my answer there. Now notice, how do we write that in using our terminology? Well, if they're not mutually exclusive, we can add the probability of A plus the probability of B. That's what we did up here and right here. But then we have to subtract the probability of A and B. And again, if we use set notation, exactly the same, except it's P of A intersect B. So use a spinner to find the probability that the pointer will stop on an odd number or a number less than 5. So an odd number are these guys. A number less than 5 are these guys. Or sorry, less than, not less than or equal to. So less than. Now, there's 2 different ways of going about doing it. You could just go up and count again 1, 3, 5, 7. That's 4 of them, plus the 2 and the 4 that we're missing. That equals 6. So we got 6 out of 8, which is 3/4. So that's one way to do it. Using the formula above, it's a little bit more complicated in this case. Like the simpler the problem is, the easier it is to do without using any formulas. But the harder the problem is, the more useful these formulas are. But I could look at this and say the probability of odd is equal to 4 out of 8, so 1/2. The probability of basically less than 5 is equal to 4 out of 8, so 1/2. The probability of odd and less than 5, basically how many numbers are odd and less than 5? That's 1 and 3, so that's 2 out of 8. So the probability of odd or less than 5 is going to equal 1/2 plus 1/2 minus 1/4. I used that as 1/4 there. So I took the 1/2 plus the 1/2 minus the 1/4, and that gives me 3/4. So that's using the formula. Otherwise, I could have just gone, okay, This one works, 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 this one works. How many do I have? I have 6, so 6 out of 8 gives me 3/4. That also works just fine. If one, so if one person is randomly selected from the population represented in this table, find the probability that the person is married or female. So married, we have 130. Female, we got 124. So the probability of married is equal to 130 out of 242. Probability of female is 124 out of 242. And so now what we gotta have to do is to figure out married or female is we're gonna add those together. Oops. And then we're gonna subtract the overlap. And notice the overlap is gonna be female and married. So female and married is that. So I end up with 130 plus 124 minus 65 over 242. You'll notice for sure I couldn't have just added those two together to start with because I end up with 254 over 242, which is bigger than 1, which can't happen. So as it is here, now I get 65, 189, I believe. 189 out of 242. All right, find the probability that a person is divorced or widowed. So again, divorced is that guy, widowed is that guy. Now notice there is these are mutually exclusive. We're either divorced or we're widowed. We're not both. So on that one, I can just add them together. I get 24 plus 14 gets me 38 out of 242. So that was A over there, and that was B. So if A and B are independent events, then probability of A and B is going to be the probability of A times the probability of B. Independent events are where the one happening does not affect the other happening. So basically one event doesn't affect the probability of the other happening. All right, so number 10, the first number 10. A U.S. roulette wheel has 38 numbered slots, 1 to 36 and 0 and 00. 18 are black, 18 are red, and 2 are green. A play has the dealer spin the wheel and a small ball in opposite directions. As the ball comes to a stop, it can land with equal probability on any one of the 32 numbered slots. Find the probability of black occurring on 2 consecutive plays on a roulette wheel. So these are independent events because what happened on the previous roll is not going to affect what happens on the next roll. So a lot of times, like people talk about the law of averages and something like that. Like, well, you know, like if I flip a coin 5 times and I got heads all 5 times, that a tails is bound to come up next. Well, that's not true, right? They're independent. A coin flip is independent of each other. The probability of getting heads on the 6th time is exactly the same as it was on the 1st time. So same thing with this. Just because if it rolls, you know, red 80,000 times in a row, as unlikely as it is, that doesn't make it any more or less likely that it'll happen on the 80,001st time that it happens. So find the probability of black occurring on 2 consecutive. Well, the first time is going to be 18 out of 38. The second time is going to be 18 out of 38. So I just multiply those two together. Then let's make it a little bit easier. That's 9 over 19 times 9 over 19. So we get 81 over 361. Is that what that is? I should double check. My mental math is not working very well right now. Well, I guess it was okay. So 361. So find the probability of a family having 4 boys in a row. So independent events, it doesn't just have to be 2. You can do it over and over and over and over again. So let's just suppose, even though it's not exactly 50-50, let's just assume that the probability of getting a boy or girl is 50-50. So that would be 1/2 times 1/2 times 1/2 times 1/2 equals 1/16. So. And that is it for probability. There's a lot more you can do in probability. Probability can get very, very hard, but we're just going to stick with the surface level stuff and making sure we understand the gist of this. And usually on the ACT, you can find a question or two on this, this level of difficulty.